let me, oops. Can you see my screen?
Yeah, we just see it well. Thank you.
Yeah. So today I'm going to speak about recent progress that past couple of years we are doing in the Illinois group, mainly by Milton Ruiz, Stu Shapiro, and Luna and San, but also in collaboration with Vasilis Paskalidis from the University of Arizona and Koji Yu from the University of Rikers. So I don't think that in this group of people I have to advertise why we study neutron stars or binary neutron stars, but let me quickly say that binary neutron stars is the only laboratory to study high-density nuclear matter and extremely magnetized actually matter. Binary neutron stars are progenitors of short gamma ray bursts, the sites of outposts heavy elements, sources of gravitational waves, as well as sources of electromagnetic emission. So my talk is going to have two parts. The main part, which is part one, is going to be about binary neutron stars and is going to touch upon different subjects like spinning binary neutron stars, magnetic field tilt, equations of state, neutrinos, as well as neutron stars in the mass gap and in relation with event GW190814. In the second part, which is going to be smaller, I'm going to talk about recent progress on computing self-consistent magnetized rotating neutron stars, as well as neutron stars that contain ergo regions and their connections to relativistic jets. So let me start with part one. Before I get into the details, I want to give you the punchline so that we can set up the discussion. First of all, with respect to the magnetic field tilt, the simulations that we have done showed three important points that I have here. First of all, the incipient jet needs a large-scale colloidal magnetic field along the orbital angular momentum in order to appear. Second, the ejecta are highly affected by the orientation of the magnetic field. And third, that the gravitational wave detectors, although in principle may distinguish effects from different magnetic field configurations, that in practice that will be difficult. With respect to the equation of state, there are 4 points to take home. The first is that the closer to the threshold value for prompt collapse, the shorter the time delay between gravitational wave amplitude, peak amplitude, and jet launching time. The second is that, again, the jet depends on the initial geometry and the seed magnetic field. The third is that the dynamical ejection of matter, again, depends with the initial magnetic field content. Finally, as a fourth message is that the post-merger frequencies are shifted due to the magnetic field. With respect to neutrinos, we have found something that is well known, that neutrino radiation reduces the baryon-loaded environment above and below the black hole that forms after the collapse of the hypermassive neutron star. Also, the neutrino radiation induces an earlier collapse of the remnant. Third, that the angular momentum losses are in general small, much smaller than the main angular momentum losses due to gravitational waves. And fourth is that neutrino radiation again affects the amplitude of the main post-merger frequency. Finally, with respect to the neutron stars that may exist in the lower mass gap between 2.5 and 5 solar masses, if they exist, the in-spiral is very similar to a binary black hole in spiral. A remnant collapses to a black hole as soon as they touch. Essentially, we don't expect any disk, escaping mass, a short gamma ray burst, or a kilonova. The gravitational wave phase difference between the binary black hole and the binary neutron star is at maximum 5 radians, which is in principle detectable by LIGO, but practically, again, it will be very difficult. On the contrary, the ring down cannot be distinguished from the ring down of a binary black hole. And finally, with respect to the event GW190814 and the 2.6 solar mass compact object that exists there, rapid rotation is one possibility. Also, it can be slowly rotating depending on the equation of state. With respect to the rotating neutron stars, I want to mention that recently we have computed self-consistent magnetized rotating neutron stars with mixed poloidal and toroidal magnetic fields that have very large values and comparable with our initial data solver, the compact object calculator. The specific geometry of those magnetized solutions can delay or accelerate the development of various instabilities. Also, as a third point is that we have found recently stable neutron stars that contain ergo regions. And in connection with the short gamma ray bursts, a preliminary work of ours showed that these kind of stars are unlikely to produce this kind of events. So this is a small executive summary. Let me start the discussion of all these subjects by some preliminary discussion about the remnant classification based on its total mass. So the remnant can be classified essentially into two categories. It's called supermassive or hypermassive. It's supermassive is a star that lies between the blue line here that I have, which is at the maximum spherical limit, and the red horizontal line, which is at the maximum mass shedding limit, which is approximately, you can think about it, that it is approximately 1.2 times 20% above the maximum spherical limit. That's one scenario. The other scenario is the hypermassive star, which are all the stars above the supermassive limit. Now, this category can be further split into two, what I'm writing here as light and heavy. The light is the one that where the mass is between the maximum supermassive and the threshold mass. The threshold mass, you can imagine that it is an imaginary mass where when you can have two neutron stars when they touch and immediately collapse into a black hole. And heavy hypermassive when the mass is above this threshold mass. Now, all these categories lead to a black hole formation, but on different timescales. Let me mention that the star which is hypermassive exists only if it is differentially rotating, while the star which is between which is supermassive, which is in this band here, it can exist as uniformly rotating also. And this can, depending where you are, this can modify the lifetime of the remnant, and you can have completely different time scales. And this is important if we want to explain events like GW170817, where we had a short gamma ray burst 1.7 seconds after the merger. Having said that as a background, I want to mention that we have done simulations with all kinds of masses, as you can see here. In the first column is a supermassive simulation. On the second column is a light hypermassive, and on the third column, a heavy hypermassive. The outcome that you can see on the third row in the bottom here is a star with some kind of collimation. And the color bar here is the force-free parameter b squared over 2 rho, which, as you can see, takes values of order 1 and therefore does not provide the conditions for the existence of a jet. On the contrary, when you have a light hypermassive case, you have a black hole after the differential rotation is washed out from the hypermassive neutron star. You have the black hole, and then the p squared over 2 rho parameter increases to value of 100 and above. And finally, when the stars, the two stars are too heavy and you have a heavy hypermassive remnant, there is no time for this kind of collimation to form, and you have nothing apart from a black hole and a very small, almost minuscule disk. And from these three categories, our favorite one is the middle one, which we have used to provide an upper bound for the maximum mass of the spherical neutron star, which is approximately 2.3 solar masses. In this slide, I want to make a little bit of a summary of spinning neutron stars, binary neutron stars. In the first topic has to do with the in-spiral of spinning binary neutron stars, where we have investigated 14 orbits with two different equations of state, the ALF2 and the SLY equation of state, and spins up to 0.32. Now, for a black hole, 0.32 is a very small spin, but for neutron stars, it's an extremely large one. And what we have found is that although tidal effects are dominant for small spins, which are of order 0.1 or below, this is no longer true when the spins are larger, like 0.2 or 0.3, which are still much smaller than the Keplerian limit. So for these are still can be considered slowly rotating neutron stars. With respect to the merger and the post-merger, with simple gamma equal 2 polytopes having spins up to 0.36, there are 4 points that I want to mention here. First, that the larger the spin, the smaller the mass of the remnant black hole and the heavier the disk, which I think it makes sense. Also, the larger the initial spin, the shorter the launching time for a jet. The second point is that angular momentum loss due to gravitational radiation is inefficient to trigger collapse of a highly spinning hypermassive neutron star. For example, for aligned binary neutron stars, where the spin is aligned with the orbital angular momentum, we have losses of the order of 13%, while for the corresponding irrotational ones, the losses are larger than 17%. The Kelvin-Helmholtz instability, when the two stars touch and the magnetic field starts to grow exponentially, is larger when you have a higher spin, which is aligned with. And also for aligned spinning neutron stars, the Poynting luminosity can be 10 times larger than the irrotational ones. And this, again, one can have all these facts in mind when he tries to explain events like GW17 or H17. With respect to the magnetic field orientation, the key, we have found that from all the previous studies, even from simple polytopes, that the key requirement for jet launching is the amplification of the magnetic field during the hypermassive neutron star epoch. And an incipient jet can be launched whether or not that magnetic field is interior, or is it like a pulsar which extends to the exterior. So the question that we wanted to ask is what happens if that magnetic field makes an angle with the orbital angular momentum. And here I have two cases. One where the dipole moment of the second magnetic field is tilted by 90 degrees. This is the picture on the left. And on the picture on the right is when both of the two dipole moments are tilted by 90 degrees. And of course, we had the case where both of the dipole moments are aligned with the orbital angular momentum. And if you evolve them, for example, I have here the evolution of these two cases that I showed. For example, after in the middle row, you can see that after 1500 M, although when for the left, where you have a mixed configuration of the dipole moments, you can see that there is some kind of organization of a magnetic field into a spiral that will lead to a jet. While on the right, where both of them are perpendicular to the orbital angular momentum, there is no such organization. And by no surprise, even if we wait very much longer, for the case on the right, we don't see a jet, while for the case on the left, we see. Similarly, here are the plots for the B²/2 rho force free parameter for the three cases. The top is when the magnetic fields are aligned with the orbital angular momentum. In the second row one is aligned and the other is perpendicular, and on the third row both of them are perpendicular. And you can see what happens here. B²/2 rho is much stronger when they are aligned, less stronger when they are mixed, and there is not a funnel at all when they are both of them are perpendicular. Here are the gravitational waves from the three cases. The top corresponds to the top figure, the blue one to the middle figure, and the purple one to the last one. And you can see nicely that how the formation of the black hole is delayed depending on the magnetic field orientation. And this can be explained because of the different viscous timescales that exist in the hypermassive neutron star remnant. Also, the jet launching time, for example, in this middle case where the dipole moments are mixed, is later than it is in the aligned case. This is not surprising given the figure that I'm showing here. And also, one can see that the other properties, for example, the ejecta and the luminosity, for the case where the magnetic fields are aligned, are larger when, for example, they are mixed. And similarly, one can see that the disk in the aligned case is smaller than the mass of the disk is smaller than the mass of the disk of the mixed configuration. All these simulations had gamma equal 2 polytopes. These are magnetized simulations with gamma equal 2 polytopes. So we wanted to somehow corroborate our results with realistic equations of state. And we started this investigation with irrotational neutron stars having two realistic equations of state and different masses in order to see all these effects with respect to the hypermassive, supermassive scenario and so on that we have discussed up until now. And there are 5 points that I want to mention. The first one is that the jets emerge from binary remnants that undergo delayed collapse, as it happens with gamma equal 2 polytopes. And those jets are consistent in broad terms with the Blandford-Snarek mechanism. Also, the closer the mass to the threshold value, the shorter the time delay between the gravitational wave peak amplitude and jet launching time. Also, the jet launching time depends on the initial geometry of the magnetic field. For example, if you have a magnetic field which is only inside the interior, it will take much longer than if you have a magnetic field which is like a pulsar. In a specific example that I can show you, it took 3 times more time. Finally, for the ejection of matter, it depends again on the magnetic field, as with the studies with simple polytopes. So here I'm going to show you very quickly two representative movies with the SLY equation of state. On the top, we have a case where the magnetic field extends to the exterior, while in the bottom it's only inside the interior. So both of them form a hypermassive neutron star. So here they merge, and as soon as they merge, even in the hypermassive neutron star case, in the case above, you see this spiral organization of the magnetic field that will lead finally to jet formation, while in the bottom, as you can see a little bit later, now you just see the pure hydrodynamical evolution in the bottom case, you will see that will take longer time, as I just discussed. So here is the magnetic field again back. the black hole forms, but when you have the black hole and the disk, there is no organized magnetic field yet. So you have to wait up until 400 or 500 M, much longer than when you have a pulsar type magnetic field, in order for this magnetic field to organize in this jet-like structure and have a force field parameter above the black hole poles that are around 100 or more. So now it starts to evolving around 400 M. And it will continue all the way up to the computational domain essentially of our simulations. On the top, you can see the disk and the jet, and there are some rotations here so that you can appreciate how it looks like from different angles. Similarly, the similar case for the bottom case where we had only the and these are the outflow of the velocities for the outflow. So both of them end up pretty much at the same state, although on a much different time scale. And this is a zoom-in version of the material around the disk. So going back into the hypermassive remnant, here I want to discuss a little bit about the rotation profile law for magnetized versus non-magnetized versions. So here in the inset, you can see the same evolution of the SLY equation of state, but with no magnetic field. And while on the main plot, you can see the evolution of the angular velocity inside the hypermassive neutron star with the magnetic field. With different lines, there are different, you can see different times. And as you can see, the differential rotation law with the magnetic field tends to be uniformly rotating inside the star, which is up until here, around 2M, while if you don't have magnetic fields, as you can see in the inset, the differential rotation law doesn't change so much. This is, and as I'm writing down here, this shows that the angular momentum redistribution from the inner to the outer regions of the hypermassive neutron stars, because of non-axisymmetric torques and gravitational waves, are inefficient mechanisms compared to the magnetic fields to remove the centrifugal support and make the star to collapse. Here I have the b squared over 2 rho factor for 3 different equations of state. The SLY, which is a relative soft equation of state, the H4, which is relatively hard, and the gamma equal 2. And you could see, you can appreciate how much bigger b squared over 2 rho is, for example, for the SLY versus the H4 or the gamma 2. Also, I want to mention that the ejecta for the pulsar-like magnetic field run was 5 times larger than the corresponding one when the magnetic field was only interior to the neutron stars. And on the bottom, you could see on the 3 panels the spectra from the SLY on the top, the H4 and the gamma equal 2 runs. Where in general the take-home message is that the frequencies, because of the magnetic fields, are essentially shifted a little bit. For example, the peak frequency or the 2+0 frequency are increased. And the magnetic field essentially damps a little bit the amplitudes of some other frequencies. Of course, these are just a handful of equations and equations of state and a handful of simulations, and one needs to do much more to find out how these trends look like, but these are indicative of the simulations that we have done. Now, recently, we have tried to incorporate a neutrino model into the Illinois GRMHD code, and essentially this was the PhD of Lunan San, who has, apart from the fluid and the electromagnetic stress energy tensor, he incorporated the radiation stress energy tensor, as you can see here. And for the radiation pressure, he followed other works, like, for example, Foucault and others, where we interpolate between the optically thin and optically thin limits. For the microphysics treatment, we have 3 neutrino species, but we don't have yet a tabulated equation of state. So in order to make some progress, we used an approximate scheme for the temperature and the energy density, which follows this simple prescription for where we decompose it into a cold part and a thermal part. And the cold part is essentially the initial data equation of state, and the thermal part is the one that you can see here. And then we have a radiation force density that includes the absorption and scattering opacities, the emissivity, and the interactions, the emission and absorption interactions and scattering interactions that you can see here. Now, from this preliminary work, we took the SLY run that I just showed you, and we inserted the neutrinos a little bit after the merger. And we watched what happens. And as you can see, for example, in the bottom, first of all, let me tell you that we again see a jet as we had with no neutrinos, which is not a surprise. The other thing is that we found what other groups have already knew, that neutrino radiation reduces the baryon-loaded environment in the polar region above the black hole poles, and this can be clearly seen in these 2 bottom plots, where on the right we have magnetic field plus neutrinos, while on the left we have no neutrinos. And you can see how the density in the funnel is much smaller on the right than it is on the left. Here is the gravitational wave signal. I will focus on the cyan one, which corresponds to the gravitational wave with neutrinos, and the green one, which is the gravitational wave with just magnetic fields. So the cyan one includes the magnetic fields and the neutrinos also. And at this black horizontal line here is the moment where we insert the neutrinos. The neutron star, the hypermassive neutron star remnant follows pretty much the same path as without the neutrinos, but it collapses much earlier, as you can see here at this moment, like 4 milliseconds before the collapse of the pure magnetized ion. So the neutrinos collapses earlier. And also the angular momentum losses because of them are much smaller, as you can see on the right panel here, which are the neutrinos are denoted by the cyan curve, and they are much smaller than, for example, the blue curve, which is the fluid, and or the purple curve, which are from the electromagnetic field. Finally, the spectrum from this single case that we ran seems very similar. The only thing, the most obvious thing that we have seen is that we found a small shift in the peak amplitude of the most prominent post-merger peak, as well as a diminishing a little bit of its amplitude, which means that it makes things more difficult for the interferometers to catch these features. Of course, a lot of things need to be done, and also a necessary resolution to study in order to understand how robust are all these results, and these will be our future investigations. Moving into now another subject, which has to do with binary neutron star mimickers as binary black holes. So the question that we wanted to ask is if we can distinguish a binary neutron star from a binary black hole, if, for example, the binary neutron star has masses that fall within the 3 to 5 solar masses. Now, there are two problems to answer this this problem. The first of all is that neutron stars are irrotational, and all the equations of state that we know, they don't support this kind of solar mass, this kind of large solar masses. The second is that if you put such a system in an orbit, it will collapse very quickly. So you have to put them in a large distance, which makes it technically difficult, both from the initial data point of view, as well as the evolution. We solved the first problem by following an idea by Evangelos Ruffini and Hartle, where we took our favorite equation of state, which was the LF2 equation of state, and replaced the inner core by a maximally stiff and compressible equation of state, which is given by this formula, where sigma, the parameter sigma, is 1, in order to have a causal equation of state. Of course, one can get, for example, a sigma equals a third and have an MIT bag model inside the Newton star. And if you do that, then the equation of state, which has this blue curve here for mass versus density, it becomes like the red curve that you can see here and can support masses even above 4 solar masses. So we, using our initial data solver, we constructed a binary with an ADM mass of a binary neutron star with an ADM mass of 7.9 solar masses, where each neutron star has compactness of 0.34 essentially at a distance at 80 kilometers. So this compactness is almost maximal, and therefore this system is as close to a black hole mimicker as one can imagine. Now, if you let this system evolve, it will, although the radius of the stars are very reasonable, around 10 kilometers, but although the distance between them are at 80 kilometers, they just merge in 3 orbits. And because of their high masses, as you can see, very shortly, as soon as they touch, they create a black hole, which rings down into a Kerr black hole. Now, the gravitational wave signal is given by here on the top left. Blue and green are 2 different resolutions, and the red one is the corresponding binary black hole with the same mass. So on the right, you can see the maximum phase difference between the 2 binaries, the binary neutron star and the binary black hole, and maximally this phase difference can reach 4 or 5 radians, which are in principle distinguishable by LIGO. On the bottom, you can see the spectrum, which is pretty much identical, and on the bottom right, you could see the dimensionless spin, which is used to compute the quasi-normal no modes, which are pretty much, according to our resolution and accuracy, they are pretty much non-distinguishable. So we conclude that it will be very difficult to distinguish such kind of events from the post-merger phase, but only from the inspiral. Now, relative to that is the event GW190814, which had a compact mass of 2.6 approximate solar masses, and there was a debate if that is a neutron star or if it is a black hole or what that is. So in this discussion that I'm going to make, I'm going to assume that it is a neutron star. And what does that imply with respect to its equation of state and spin? So from different estimates about the mass, we have found that the mass, the maximum mass of a neutron star is approximately 2.2 or around 2.3 from the earlier considerations that I have talked about, and which means that this star can be a rapidly rotating neutron star. But the question is that if rapid rotation is the only possibility, So for example, if you have a soft equation of state like the SLY that we have talked before, here again with the black curve is the spherical limit, and with the red curve is the mass shedding limit. So if you have a soft equation of state, this the mass of that companion lies above the mass shedding limit. So even if you put it to spin as fast as possible, that equation of state cannot explain that neutron star. On the contrary, if the equation of state is a little bit stiffer, of course, depending where on the density you exist, if you are close to the mass shedding or close to the turning point line here, you can have a neutron star which is even slowly rotating. So all possibilities are open for this neutron star. It can be since rapid rotation may not be sufficient, and rapid rotation may not be even necessary. Moving to the second part, as we all know, neutron stars have enormous magnetic fields, orders of magnitude than the strongest MRIs that exists in all the hospitals in the world. And in all the works that we have talked about up until now, the magnetic field is treated artificially, which means that we put it by hand. So in order to understand better extremely magnetized and strongly gravitating matter, we want to in the future to do this self-consistently. And we embarked into a program with our compact object calculator code to solve for this kind of magnetized neutron stars with generic magnetic fields. So here, for example, on the plot on the bottom, I have some models where we have computed where the toroidal magnetic field is as strong as the poloidal magnetic field. The toroidal magnetic field is given by the upper panel. It's the By component, and it's of the order of 10 to the 17. And it's similar to the poloidal field on the bottom panel. In order to do that, we solve the 3+1 decomposed Maxwell equations together with the full set of Einstein equations, and not just so we don't solve the conformal sandwich, but we use the waveless formulation to solve for essentially all the components, including the gamma ij's of the Einstein equations. So we have computed both normal stars and supermassive stars. On the top, for example, you can see the poloidal magnetic field with the arrows and the toroidal magnetic field with the densities. The toroidal magnetic field, as you can see, is very high, close to the surface of the star on the equatorial plane. And similarly, you can see it here. For example, the toroidal magnetic field is this, for this model is here, and the surface of the neutron star are denoted by the vertical dashed lines. So the toroidal magnetic field peaks the maximum value just below the surface of the neutron star. And also you can see here the surfaces of the electromagnetic components of the electromagnetic vector AT and A5. Now, one of the extreme solutions that we were able to compute has the following artifact. Actually, before I mention that, let me tell you that the black contours that you see here are contours of density. And if you, maybe you cannot see it very clearly, but if you zoom into this area here, you see that the contour density makes a kink. Now, I zoom in here on this bottom left corner at x over r equals 1 is the surface of the star, and you could see that inside the neutron star, because of the extreme magnetic field, the matter is expelled. It essentially goes to zero. The density goes to zero inside the neutron star and creates a toroidal coil, essentially, which is the strongest toroidal coil in the universe. We have evolved a number of those models. Here is the model, one of them, which has been evolved up to T over m equals 600, which corresponds to approximately 10 of n time scales. And on the top row you see the equatorial plane. On the bottom row you see the azimuthal plane. On the top row, in both planes with black lines, you could see where the magnetic field is strong. And you could see that the black circular lines here is where the toroidal magnetic field is strong. And similarly, the black lines here is where the poloidal magnetic field is strong. These are uniformly rotating stars for the moment, and they exhibit a number of oscillations. And at the end, after 10 or 10 times, although the magnetic field, pretty much as you can appreciate here, it holds its structure, it succumbs to the typical varicose and kink instabilities that have been exhibited by other simple models. So there is a lot of work to be continued in this area.
Tony, Manuela
yes.
here. You have 5 minutes, so I would recommend to leave a little bit of time for questions.
Definitely. I think this is my last topic, and I will finish very soon. So this is an older subject which has to do with stars that contain ergo regions, and essentially the question is if the ergo region has any effect in the creation of jets, and can we have stars or some object with an ergo region that creates a jet? That was the motivation of this whole project. The first thing is that we had to find stars that are stable and contain an ergo region, and we managed to do that. Here is a star that rotates up to 30 rotation periods and holds its ergo region, which is this toroidal region that you can see here. It is held perfectly well, so it's totally dynamically stable. We have investigated the parameter space of these ergo stars, and we found them that most of them are dynamically unstable. Some of them exist as hypermassive differentially rotating neutron stars. And now the whole point is that if we do this simple thought experiment, where we thread this star with a magnetic field, what is going to be the outcome? And just to finish the talk, this is going to be the outcome. In the top row, I have the evolution of a normal star. On the right column is the density. On the left column is the density. On the right is the p square over 2 rho factor. In the middle row, we have the evolution of the ergo star, and in the last row, we have the evolution of a black hole, typical black hole with a disk. As you can appreciate from the right column, the ergo star is very similar to the normal star and very different with the black hole disk, which means that from this preliminary investigation, we think that it's very unlikely that an ergo region will play a role in the creation of short gamma ray bursts, for example. That's it. Thank you very much, and I'm happy to answer any questions.
Thank you very much, Antonios, for this very beautiful, impressive talk reviewing your research and the research at the University of Illinois. We have now 15 minutes for discussion and question before we have our next speaker, Tsokaros. So I would like to encourage people to raise their hand, and I see already one, Julian.
Mm-hmm. Yes. So I was intrigued by the simulations contrasting magnetic fields that were either entirely held within the star or extended outside. Okay. And a couple of questions related to that. One is you didn't speak about the intensity of the magnetic field, either inside the star or outside. And the other is I'm curious about the prehistory of the neutron star that would lead to a field entirely confined within its body.
Yeah, with respect to the first, can I answer?
Sure, Joe, go ahead, yes.
Do you hear me?
Yes, we do.
Oh, okay. So with respect to the question about the intensity of the magnetic field, in both cases is the same, which is approximately, we start with magnetic fields that approximately are 10 to the 15 Gauss. And I can, if you think that is a large value, I can explain further why we pick. But yes, both of them, they have the same intensity, both the one that extends outside and the one which is only inside. And the second, the question regarding the second question is purely a point of principle. It's not motivated by any kind of a physical, argument, but because the evolution of the magnetic fields, together with the general relativistic equations, are generally difficult. Traditionally, people have started with only interior magnetic fields, and then we moved into the interior plus exterior magnetic fields. So it's only as a point of principle.
Okay, so I see Maria.
Yes, I have a question. I know that some other groups, like Valenzuela's group, doesn't see any kind of influence of the initial magnetic field after the black holes collide during the scrambling of the magnetic field during the collision. I would like to see what is the
May I ask to repeat? You said when two black holes collide, or did I?
No, I'm sorry. I'm just catching my breath. Okay, so Valenzuela's group clearly showed that the initial magnetic field configuration doesn't have any influence in the collision of two neutron stars, because during the collision, the magnetic field is so scrambled and amplified that every information is erased. On the contrary, you showed a very strong influence of the magnetic field of neutrons, initial magnetic field of the stars on the remnant. So what is your comment on this regard?
Oh, the comment is very simple. It's they haven't done evolutions of external of collisions with external magnetic fields.
Okay, that's all.
As far as I remember, unless I have missed some kind of a paper.
Okay. Well, that might be all. Okay, I'll check more about this.
Let me know if that exists, but yeah, I think, yeah.
All right, so I see more hand raised. Zach, and then Prasad.
Yeah, hi, Antonios. Can you hear me okay?
Yes.
Awesome. Yeah, excellent talk as always. So I do have a question about the exterior magnetic fields. So, right, we would expect the plasma in the exterior to have some degree of co-rotation, one would expect. And my first question is, did you model any co-rotation of the plasma in conjunction? Okay, so in other words, as soon as the simulation starts, the magnetic fields will start to then become, the exterior magnetic fields will start to become dragged.
I'm pretty sure that you know, since you yourself developed this code, I'm pretty sure you know it much better than me. So,
not this part, but yeah, I was just curious about that detail of the prescription, because right, suddenly things become a lot more complicated if we
that's right.
Try to co-rotate the exterior, because we hit a light cylinder pretty quickly.
And this is something that we want to improve, especially with the self-consistent models that we are evolving, in order to be more accurate in the evolutions of these models, because it's very important now.
Yes, absolutely. And then just a second question regarding the self-consistent magnetic field initial data. Have you performed like convergence tests to confirm that in fact there are no, say, GRMHD instabilities that arise as soon as the evolution begins with the prescribed magnetic fields?
We have done convergence tests, but they are limited into different parameters of the initial data. Now, when the fact that you have, as you know, some initial data doesn't mean that they are stable. I can construct a simple rotating star, like a spherical star, simple spherical star with no rotation, and it can be unstable just because I put the density too high. And unfortunately, there's no such theorems for the magnetic fields. So somehow we are on the blind as far as the stability goes and what goes on when you start evolving things. So we just, as far as I know, I'm not familiar for any theoretical progresses regarding that area. And the only way, it seems to me, it's just do a parameter study and see what looks to be stable and what doesn't.
Yeah, I tend to agree with that approach. So yeah, thank you, Antonios. Again, excellent talk.
Thank you.
Yeah, my question may be a bit naive, but I wanted to know that at end of neutron star merger simulation, do hydrodynamically stable neutron stars get formed, or all neutron star merger simulations lead to only black holes at the end?
Oh, it can. For example, let me. So these three cases are the three cases between these three numbers here above and above the threshold. There is a possibility that the remnant is below this horizontal blue line. Now, if the remnant by some reason, which is very low neutron stars, end up here, when it loses all its rotation, it will hit the spherical limit and it will stay forever as a stable spherical neutron star. So that's a fourth possibility, which I didn't mention here because the possibility of that happening is very small. So I only mentioned the three more likely possibilities.
Has that been seen in simulations that by evolving it for quite long time, do hydrodynamically that system gets stable, that we get a stable neutron star at the end, that it don't collapse?
Our group hasn't performed any such kind of simulation. Yeah.
Okay, so we have Jay Kalinani next.
Hi, yes, thank you for the very nice talks. I had a couple of questions, very naive ones. The first was to confirm, so what is the initial magnetic energy corresponding to the intensity that you talked about? Was it around 10 to the power 49 to the power 50 ergs for the magnetized simulations? And my second question is a bit more naive. So you mentioned that there was this case where there were neutrino radiation active and the collapse was sooner compared to the case where there was no neutrino radiation. So, but there was no change in the angular momentum of the remnant. So in that sense, but there was no neutrino effect on the angular momentum of the remnant. So what drive the earlier collapse? Thanks a lot.
Let me start with the second question, because the first one I have to ask you to repeat it. The second question regarding the neutrinos is, although there is no losses with respect to the angular momentum due to neutrinos, this does not mean that the angular momentum in the hypermassive neutron star does not change because of neutrinos. The fact that the hypermassive neutron star with neutrinos collapses earlier without is because, indeed, this is exactly what it happens. The differential rotation, although I haven't showed it here, but similar to the transparencies that I showed with the magnetic field, with and without magnetic field, when you have neutrinos, because of the diffusion, the differential rotation law inside the neutron star changes, and this is what triggers collapse earlier than without the neutrinos. Good thing that you mentioned it, although I haven't included it in any of my plots. Now, with regard to the first question, can you repeat it, because I didn't understand it?
Oh yeah, thanks for the answer. And yeah, my first question was related to what is the corresponding initial magnetic energies that you start with in your simulations. You mentioned that the magnetic intensity is about 10 to the power 15 Gauss, but so the corresponding magnetic energy should be like around 10 to the power 49, 10 to the power 50. Ergs.
Yeah, I have to I have to check the plots. Also depends when you, for example, if you put the magnetic field when you insert, because in all these cases you insert the magnetic field by hand. And typically, when we insert the magnetic field by hand, what we try to control is not the magnetic energy itself, but the ratio of the magnetic pressure over the gas pressure. And typically for all these cases, we use the magnetic pressure to the gas pressure to be of the order of 10 to minus 3, so that the magnetic field is dynamically unimportant. It doesn't change the neutron star configuration. Now, the magnetic energy, I think before I say something which is not correct, probably it's better if you check the plots, which I remember that they exist in all our papers, but it's pretty much close to the values that you mentioned.
Okay, thanks a lot. Thanks a lot.
Yeah.
So we have Udi. That's one last question. Udi, you can ask your question.
Thanks. About the magnetic field, maybe you already answered. If I understood correctly, you said that the strength of the magnetic field is about 10 to the 15 Gauss.
Yeah.
Strengths. And you said that you will explain why you choose it like this, and I don't remember that you did. It seems to me to be a bit high compared to what you expect before the merger.
Yeah. It's very high, and the reason is our weakness to do high resolution simulations. One of the previous attendants mentioned the papers, a paper by the group by Palenzuela, who recently have done some simulations where the step element delta X inside the neutron star was approximately 37 meters. And even earlier, there are simulations by Cucci where they have gone to 15 or 17 meters, if I remember correctly. And those simulations have shown that even if you start with a small magnetic field, which is of the order of 10 to the 11 or 10 to the 12, when they merge, immediately in less than a millisecond, that thing exponentially goes to 10 to the 15th. But in order to capture that, you need high resolution in order to capture the so-called Kelvin-Helmholtz instability and other instabilities, the MRI and so on and so on. So we cannot afford this kind of simulations, high resolution simulations, although we used most of the simulations that you have seen, they used high resolution, which is approximately 90 meters. But still, this is not high enough in order to capture these magnetic fields. So in order to skip that step of the exponential growth of the magnetic field when the two neutron stars touch, we start immediately with a magnetic field which we know it has been reproduced by the other groups like the groups by Palenzuela and Cucci, and that's why.
Well, correct me if I'm wrong. I would expect that the magnetic field which is growing up on a time scale of millisecond will be small scale, and the magnetic field that you start with are large scale. And as you show, the configuration of the large magnetic field is very important, even dynamically for the dynamic ejecta. So there might be a big difference between large field on small scale and large field on large scale. Am I missing?
Well, there may be many things, but what I can tell you is that there are two groups that they have performed high resolution simulations, and this is exactly what they see. And
they find magnetic field on large scales after a millisecond?
Yeah, essentially very in a time scale of a millisecond. Yes.
All right, Udi. Since it's your turn, I believe, I think we're done with the question. Is actually